ground fault protection was introduced to mitigate arc-limited faults. These types of faults can cause failures while remaining below the tripping threshold of standard circuit breakers. The arc-limited fault current changes depending on the voltage level. At 480 volts, the arc-limited fault current is approximately 89% of a bolted fault current. At 208 volts, it drops to about 50% or less of a bolted fault current, and at 120 volts, it's roughly 10% of the bolted fault current. Arc flash calculators and formulas don't typically consider a minimum voltage for calculations. It's crucial to understand that at lower voltages, the potential arc flash energy is significantly reduced. For arc-limited faults, it's recommended to implement a ground fault protection level of 1 second or less. This is because in arc-limited fault scenarios, the main breaker might not trip on overcurrent, but the ground fault protection should activate. For more detailed information on arc-limited faults and ground fault protection, firstly, you can refer to IEEE Standard 1584-2018, which provides guidelines for performing arc flash hazard calculations. Secondly, the National Electrical Code, specifically Article 230, covers service conductors and overcurrent protection, which is relevant to ground fault protection. Thirdly, consider reviewing Eaton's Ground Fault White Paper, which offers insights into ground fault protection strategies. Understanding ground fault protection requires considering several factors. Firstly, the bolted fault current needs to be determined. This is the maximum current that would flow in a direct short circuit without any arc resistance. This value is used as a reference point for estimating the arc fault current. Secondly, the voltage level plays a significant role. As mentioned earlier, low voltages tend to have lower arc fault currents. Thirdly, the type of equipment and its configuration influence the arc impedance. Enclosed equipment might have a different arc impedance than open-air systems. When performing arc flash calculations, even though some calculators might not directly account for minimum voltage, it is important to consider the reduced arc fault current at lower voltages. This will affect the incident energy and flash protection boundary calculations. The selection of an appropriate ground fault protection level involves balancing safety and system coordination. A faster clearing time, such as 1 second or less, reduces the potential for damage and injury. However, it's crucial to coordinate the ground fault protection with other overcurrent devices in the system to avoid nuisance tripping. Coordination studies should be conducted to ensure that the ground fault protection operates only when a genuine ground fault occurs and not due to normal system disturbances. The National Electrical Code provides requirements for ground fault protection in specific applications. Article 230.95, for example, addresses ground fault protection of equipment for services. These requirements aim to minimize the risk of equipment damage and fire hazards caused by ground faults. Ground fault protection systems typically consist of a ground fault sensor, a relay, and a tripping mechanism for the circuit breaker. The ground fault sensor detects any imbalance in the currents flowing through the phase conductors, indicating a ground fault. The relay processes a signal from the sensor and initiates a trip if the fault current exceeds a predetermined threshold. The tripping mechanism then opens the circuit breaker, interrupting the flow of current to the faulted circuit. Arc flash hazards are a serious concern in electrical systems. Arc flash events can generate intense heat, pressure waves, and toxic gases, posing significant risks to personnel. Therefore, it is essential to implement appropriate arc flash protection measures, including ground fault protection, to minimize the likelihood and severity of these events. In addition to ground fault protection, other arc flash mitigation techniques include using arc-resistant switchgear, implementing remote racking procedures, and wearing appropriate personal protective equipment, or PPE. Arc-resistant switchgear is designed to contain the energy of an arc flash event, reducing the risk of injury to personnel. Remote racking procedures allow operators to operate circuit breakers from a safe distance, minimizing their exposure to arc flash hazards. PPE, such as arc-rated clothing, gloves, and face shields, provides a barrier of protection against the thermal effects of an arc flash. The IEEE 1584 standard provides guidance on performing arc flash hazard calculations and selecting appropriate PPE. The standard outlines methods for determining the incident energy and flash protection boundary based on the system voltage, fault current, and clearing time. It also provides recommendations for PPE selection based on the calculated incident energy. Ground fault protection is not a substitute for other safety practices. It is essential to follow safe work practices, such as de-energizing equipment before working on it and using appropriate lockout-tagout procedures to prevent electrical accidents. Regular training on electrical safety is also crucial for ensuring that personnel are aware of the hazards and know how to work safely around electrical equipment. In summary, ground fault protection is an important component of electrical safety systems. It helps to mitigate the risks associated with arc-limited faults and arc flash events. By understanding the principles of ground fault protection and implementing appropriate measures, electrical professionals can create a safer working environment. It is important to consult with qualified electrical engineers and safety professionals to ensure that the ground fault protection system is properly designed, installed, and maintained. Regular testing and maintenance of the ground fault protection system are essential to ensure its reliable operation. Testing should be performed in accordance with manufacturers' recommendations and applicable standards. The ground fault sensor, relay, and tripping mechanism should be inspected and tested to verify that they are functioning correctly. In conclusion, the application of ground fault protection is a multifaceted issue that requires a thorough understanding of electrical systems, fault characteristics, and safety standards. By carefully considering these factors and implementing appropriate measures, it is possible to minimize the risks associated with ground faults and arc flash events. Remember to always consult with qualified professionals and adhere to relevant codes and standards to ensure the safety of personnel and equipment. Further research can be conducted in understanding ground fault protection schemes and their implementation in electrical systems. Firstly, differential protection schemes can be researched. Differential protection is a form of protection that operates based on the difference in current entering and leaving a protected zone. It's highly sensitive and selective, making it effective for detecting faults within the zone it protects, such as a transformer or a generator. Secondly, high-resistance grounding systems are worth looking into. High-resistance grounding is a method of grounding electrical systems that limits the ground fault current to a low value. This can reduce the risk of arc flash and equipment damage during a ground fault. Thirdly, solid grounding is a good subject to understand as well. Solid grounding involves directly connecting the neutral point of a system to ground. This provides a low impedance path for fault current, which can help to quickly clear faults and minimize voltage rise during a ground fault. Fourthly, look into ungrounded systems. Ungrounded systems do not have a direct connection to ground. While they can offer some advantages in terms of service continuity, they also pose challenges for ground fault detection and can lead to overvoltages during ground faults. Fifthly, the use of ground fault circuit interrupters, or GFCIs, in residential and commercial settings should be examined. GFCIs are designed to protect people from electrical shock by detecting small ground faults and quickly interrupting the circuit. They are commonly used in bathrooms, kitchens, and outdoor areas where there is a higher risk of electric shock. Sixthly, the coordination of ground fault protection with other protective devices such as overcurrent relays and fuses is critical for ensuring that the system operates correctly and that faults are cleared quickly and safely. Coordination studies should be conducted to determine the optimal settings for each protective device. Seventhly, the impact of harmonics on ground fault protection systems should be understood. Harmonics can cause nuisance tripping of ground fault protection devices and can also mask legitimate ground faults. It's important to consider the presence of harmonics when designing and setting ground fault protection systems. Eighthly, the use of ground fault monitoring systems can provide valuable information about the health of an electrical system. These systems can detect insulation degradation and other potential problems before they lead to a ground fault. Ninthly, the requirements for ground fault protection vary depending on the application and the applicable codes and standards. It's important to be familiar with the specific requirements for each situation. Tenthly, it's important to stay up to date on the latest advances in ground fault protection technology. New technologies are constantly being developed to improve the performance and reliability of ground fault protection systems. Lastly, it is important to reiterate that if any of this doesn't make sense or is not fully understood, it is best to consult with a licensed professional and not to attempt to perform any electrical work without the appropriate safety equipment. In addition to the resources listed, you can also find valuable information on ground fault protection and arc flash hazards from organizations such as the National Fire Protection Association, or NFPA, the Institute of Electrical and Electronics Engineers, or IEE, and the Occupational Safety and Health Administration, or OSHA. These organizations offer training courses, publications, and other resources to help electrical professionals stay informed about the latest safety practices. Additionally, many manufacturers of electrical equipment provide technical support and training on their products. This can be a valuable resource for understanding how to properly install, operate, and maintain ground fault protection systems. It is important to remember that electrical safety is a shared responsibility. Everyone who works with or around electrical equipment has a role to play in preventing accidents. By following safe work practices, using appropriate PPE, and staying informed about the latest safety standards, we can create a safer working environment for all. This includes, but is not limited to, firstly, regular inspection and maintenance of electrical equipment can help identify and correct potential problems before they lead to a ground fault or arc flash event. Secondly, proper labeling of electrical equipment can help workers understand the hazards and how to work safely. Thirdly, effective communication between workers is essential for ensuring that everyone is aware of the potential risks. Fourthly, a strong safety culture within an organization can help promote safe work practices and prevent accidents. Fifthly, it is important to encourage workers to report any safety concerns or near misses so that they can be addressed promptly. Sixthly, it's important to provide workers with the necessary resources and support to work safely. This includes access to training, PPE, and other safety equipment. Seventhly, it is important to recognize and reward safe behavior. This can help to reinforce the importance of safety and encourage workers to follow safe work practices. Eighthly, it is important to learn from past accidents and near misses. This can help to identify areas where safety can be improved. Ninthly, it is important to continuously improve safety programs. Safety programs should be regularly reviewed and updated to reflect the latest best practices. Tenthly, it's important to have a plan in place for responding to electrical emergencies. This includes knowing how to shut off power to the affected area and how to provide first aid to injured workers. Ground fault protection is a critical component of electrical safety systems, but it is only one part of a comprehensive safety program. By implementing a holistic approach to electrical safety, we can create a safer working environment for all.